So far, what we know, for instance, is that 1 mole of any substance is going to be, for the remaining of this course, equal to 6.02 times 10 to the 23rd of anything. So I'm not going to put units. I could say items, particles, atoms, molecules, and then the same here. But I'm just going to keep it there as a reminder of what is coming after this idea of empirical formulas. So keep it right there as a reminder. Now, if you look at a chemical formula, and let's start with an easy one. That happens to be a real formula for a compound known as methane. Now methane at room temperature is always a gas. And we indicate that by writing a small g in front of the formula of the chemical. Now, methane, you may or may not know, is a gas that can be used for heating, for combustion, pleasure. Not commonly done, but you can actually burn it. To burn it, you need to do that in the presence of oxygen. Now, as I said last week, oxygen, when it's found by its own or on its own in a reaction, is always written as bimolecular or dimolecular. Never just simply O, always O2. And that's the case for hydrogen alone and for nitrogen alone. Also at room temperature, this is always a gas. So if you apply a certain push for these two to combine, and by that I mean if you, for instance, use a spark, use a match to get the reaction going because it needs an extra push. What happens is that these two combined, we actually call this a combustion. This burns in the presence of that, and the products are always the same. Carbon dioxide, another gas at room temperature, and water. Now, because this is happening at a high temperature, since this is burning, the water is often also a gas. But it immediately cools down to a liquid when done, at room temperature. Now, this is a generic formula for a combustion. Which is a type of reaction. We're going to talk about types of chemical reactions in chapter 8, I believe. And if we count atoms in every one of these molecules, we're going to find out that it may be okay the way it's written, or we, the chemists studying the reaction, have to fix it. What do I mean by that? Well, there is this idea of the conservation of mass. That tells you that in this known universe of ours, we cannot create nor destroy matter. In this case, mass stands for matter. We can only change it. As chemists, we can change these. We can combine these two and change them into these. But the amount of matter cannot be more or less than what naturally it would have to be. So because of that, we have to always make sure that not only we use the right formulas for the right chemicals, but also the right amounts. And that's key. This idea is going to give you a skill known as balancing chemical equations. So this is a chemical equation. Guys on this left side are called the reactants. I'll label them later, not right now, because we're talking about something that is one of the last topics of the chapter, And I want to leave the idea of labeling this for a little bit later. But these are called reactants, these are called products, and the amount of every single atom has to be the same on both sides when you tally all of them together. So let's do a tally of carbon, hydrogen, and oxygen on both sides of the equation and see what we end up with. So on this side, if we look at this first molecule, we have carbon, and we have only one carbon, right? There's an implied one there. So we have one atom of carbon, which in essence is also one mole. I mean, there are very, very different amounts, but it's saying the same. So I can read these as being one atom or one mole. Now, is there any more carbon on the other chemical that is reacting? And the answer is no, there's no carbon there. So that's it. That's the total amount of carbon on this side of the equation, on this side of the chemical reaction. On the other side, better be the same amount. If not, we have to fix it. So if we start counting carbon, we have one atom or mole of carbon right there. There's a one implied. There's no more carbon here, there's no carbon there, so that's it. There's no more carbon. So far so good. It looks like we have a chemical reaction that seems to be written properly. Now let's count hydrogen, because it's the next one that shows up here. So we have a 4 in front of the H, and that tells you that there's 4 of these. So we have hydrogen, and we have 4. We have 4 what? 4 atoms in one molecule of methane, or 4 moles of hydrogen in one mole of methane. So we're going to say 4 atoms, or moles also. We're going to be counting from now on, after we finish with this explanation, in moles only, not atoms. So that's why I want to emphasize the fact that an atom and a mole in this context are equivalent. Not the same amount, but the same interpretation. Now there's no more hydrogen here, right? That's it. We have 4 hydrogens total on the left side of this arrow, of this chemical reaction. On this side, there's no hydrogen on the first chemical involved in the product side, but there's 2 here. There's a 2 right there. So hydrogen, we have 2 atoms or moles. And here we have a problem. So the equation, the chemical reaction as written, is properly written because this is the right formula for methane, this is the right formula for oxygen, that is correct for carbon dioxide, and that is correct for water. But the amount of each of these is not properly written, and we need to fix that ourselves. It's like, and maybe this is not the best analogy, but it's the one that I use every year. If you need to make pancakes, and I guess some people call them differently, hot cakes, Johnny cakes, I don't know. But those are the wrong things that some people make for breakfast. You need ingredients, right? So pancakes are the outcome of your prepping. At least in my household, what we do is it's very simple. You buy the prepared flour, the so-called biscuit, which is a brand, and we combine, well, that's what I've always done with my wife, 1 cup of flour plus 1 egg, plus maybe 1 cup of milk. I hope that turns out into decent pancakes. But the point that I'm trying to make is that by combining these 3 things, I don't know, depending on the size, of course, of the pancakes, but let's say that we all make them the same size and always the same way. Let's say that we get 12 pancakes, very tiny, or 6 middle ones, whatever. The point is that 1 cup of that, 1 cup of that, and 1 egg gives you 12 pancakes. If I don't have 1 egg, I cannot make 12 pancakes, right? If I only have 0.5 eggs, 1/2 an egg, I'm at a block. Maybe that doesn't work very well as an analogy. Let me put it back as 1 egg. But if I only have 1/2 cup of milk, I don't have enough to make 12 pancakes. I need to fix the recipe and say, no, I need 1 cup. This recipe as written is wrong. I have the right ingredient, cup of milk, milk, but I need 1 cup, not 1/2 cup. So I fix that, and that balances that. Now, of course, if I want to make 24 pancakes, I hope you immediately see that you have to double everything. You need 2 eggs, you need 2 cups of flour, and you need 2 cups of milk. If you only have 1 cup of milk, you cannot make 24 pancakes. You need to adjust that. That's more or less what we're doing here. If we want to burn 1 methane molecule with oxygen, we produce these. But we don't have enough of these being produced. We need to fix that. We need to fix the recipe, if you will. So we're just looking at ingredients and products of our recipe. So let's try to fix it. It's actually not that complicated as it sounds. If I have 4 atoms of hydrogen on this side of my reaction, and these are the correct formulas, the only thing I can do to fix the formula is not changing the ingredient. The ingredient has to be still water, or the product of the recipe. But I can alter the amount. I can say, you know what, with 1 methane, I produce not 1 water, but I actually produce 2 waters. So how do I indicate the amount? By using something called a coefficient, which is a number in front of a chemical, not as a subscript, not as a superscript, but in front of the whole chemical, like so. So this is called a coefficient. And those are fine to add or remove as well, until you have a conservation of mass, a balanced equation with the same amount of every element on both sides of this arrow. So feel free to play with those numbers until you get the amounts of each chemical balanced or to be equal. Now when I added that 2 here, basically what I'm saying is that I have H2O plus H2O. I have 2 of those. 1 egg, 2 eggs, 1 water, 2 waters. If I add the total amount of hydrogen on these 2 waters, I have 2 plus 2, 4. So I can change this to 4. And I guess automatically, now we have 2 water molecules being produced from 1 molecule of methane using the proper formulas for water, CO2, oxygen, and methane. And all of a sudden, we have also the same number of hydrogen atoms on both sides of the equation. So this is said to be balanced. We didn't change the amount of carbon because that's in a different ingredient. So we're still fine there. But we have accomplished balancing the water, or having the right amount of water. Now we're done with hydrogen because now we have it balanced. We have one more element to double check, and that is oxygen. So we have oxygen here. We need to write it as a symbol to count atoms, because in this case we're just accounting, not writing formulas. And this 2 tells me that I have 2 O's. So there are 2 atoms or moles of oxygen in 1 unit of O2. On this side, I have 2 here. So oxygen, I have 2 right there. But I'm not done because there's also oxygen here, right? And I just added a 2 to water, so if I count the oxygen on 2 water units, I have 1 plus 1, 2. So I have 2 more coming from different places, for a grand total of 4 atoms or moles of oxygen. And on this side I have 2 only. So that cannot happen. That's again, like I have my recipe wrong. I need to add more of the ingredients to make my product, my pancakes. And that is actually also fixable by putting a coefficient. So I can put a number here because it doesn't change the chemical, it just changes the amount. This is still eggs or milk. What we need to decide is if we need 1 egg, 2 eggs, or 3 eggs, or 1 cup, 2 cups, or 3 cups. Now, what's my goal? I need a grand total of 4 atoms of oxygen because that's what I have on this right side of the equation. So how do I do that? What number do I put here that will give me 4 as a grand total? 2. A 2. This is not 20, this is 12. 2 times 2 is 4. Now we have fixed this so that we have 4 atoms of oxygen in 2 molecules of O2. And now we can compare, and we have 4 here, we have 4 there, we have balanced that. Now we didn't touch anything else. When we added the 2 here, we did not touch that, we did not touch these, we did not touch the water. That 2 had been added in the previous step. So now we have the right amounts of ingredients with the right amounts of products on both sides with the proper formulas, because we always start with the proper formulas. And if we do the accounting again, it's gonna be equal on both sides. So 1 carbon, 1 carbon, 4 hydrogens, 2 times 2, 4 hydrogens, 2 times 2, 4 oxygens, 2 plus 2 times 1, 2 plus 2, 4 oxygens is said to be the correct balanced equation. So this is the word I'm using. In other words, we have fixed the recipe. We had the right ingredients, but not the right amounts. Okay? So we're going to be doing a few problems of this nature. But I want to show you another reaction. It's still going to be a combustion, but it's going to be a different chemical that we're going to burn. Which is going to give me the opportunity to talk to you about empirical formulas, that topic that sometimes is a little tricky. So I'm going to write a formula for a different chemical. C2H8. We're still going to burn it. Still a combustion. We're still going to produce carbon dioxide and water because that's the product always of combustions. These are all still gases. I'm not going to bother with that right now. You already know that that's important, but we're not going to write it for this. Now, before we talk about empirical formulas, let's see if we can balance this equation, this chemical reaction, as we did before. So, how many carbons do you see on this side? 2. We have, I'm just going to write now 2C. And on this side?
2. 1.
Only 1. I agree, only 1C. So, right at the beginning, we realized, well, we have 2 carbons on the left side of the arrow and only 1 on the right side, on the product side. So we need to fix that. We can always add coefficients. So if I want 2 carbons on this side The only thing that I should do is put a 2 in front of it, because that will tell you that we have now CO2 and CO2, two of them combined. And that will give us 2 carbons. We did not change the formula. The formula is still CO2. We just got twice as much. Now let's take a look at the next chemical. Hydrogen. There's 8 hydrogens on the left. And if we go to the right, how many do we have? Only 2. So we have only 2 hydrogens. We need to fix that again. We cannot touch the formulas, only the amounts of the chemicals. So how do we make these 2 become 8? We put a 4 in front of it. There's nothing wrong with that. And when we do that, we have now H2O, H2O, H2O 4 times. And if we add all of the H's here, we get, instead of 2, 8, which is the same amount that we have on the other side. And now we have fixed the hydrogen. We have also fixed the carbon because we did it first. And now we go to the next chemical. We're done with these. Carbon and hydrogen are balanced. Carbon and hydrogen are balanced. We looked at oxygen. Well, we see a 2 in the subscript, indicating that there are 2 grand total of oxygens. 1 molecule of O2, but 2 moles of individual oxygen atoms in 1 molecule of oxygen. How many do we have on the right? Well, let's count it. 2 times 2 is 4. 4 times 1 is 4. That's not 40, but 4O plus 4O is 8O. So we have 8 oxygens on the right and only 2 oxygens on the left. We need to balance that too. What do we need to change the amount of? Well, I hope you see that it's this one that we can change, because we already have 8 over here. We need 8 over here. So what do we do? Put a 4 in front of the O2. And that will give you 4 times 2, 8 oxygens, which is what we have already over here. We haven't touched anything else. Now we can take a step back and see, wait a minute. So I had the carbon balance before. Is it still balanced? Yes, 2 carbons, 2 carbons. Is the hydrogen balanced? 8 hydrogens, 4 times 2, 8 hydrogens. It is balanced. Is the oxygen okay? 4 times 2, 8 oxygens. 2 times 2, 4, plus 4 times 1, 4, 8. It is balanced. Now, this is different than that because these are 2 different chemicals. This would be called ethane. It's a different gas. Still, you can burn it in the presence of oxygen and produce the same product. But you produce different amounts because you have more carbon here, you're producing more carbon there. I can keep going with other molecules that have the same general formula. Let me show you one more. We're not going to balance this one. I'm just going to show you that there's actually, this keeps increasing, C3, H12. That I can combine with oxygen, produce carbon dioxide and water. But the point that I want to turn your attention to is the following. You see, these 3 chemicals are very different. They're 3 different gases with 3 different boiling points, amounts of carbon, amounts of hydrogen, etc., etc. However, they do have something in common. The proportion of carbon to hydrogen is the same. For every 1 carbon, there's 4 hydrogens. For every 1 carbon, there's 4 hydrogens. For every 1 carbon, there's 4 hydrogens. That's what is known as the empirical formula. So, I could write down, let me put here the name that I'm going to be using. Empirical formula. Your book defines that, okay, my glasses, on page 197 as, I hate the definition, but I'm gonna read it to you. The formula that represents the lowest whole number ratio of the atoms in a compound. The formula that represents the lowest whole number ratio in a compound. So, the empirical formula for these three gases is exactly the same. I'm just going to read those three formulas. So, these three, if you would try to reduce them to the simplest ratio of carbon to hydrogen, all three would be written as CH4. Now, this is not a molecular formula. These are molecular formulas. These guys right here. This right here is an empirical formula for all three of them. All three of them have the same basic composition, basic ratio of carbon to hydrogen. Now, how do we get an empirical formula, and then how do we get a molecular formula? Well, let's find out. According to your book, and they start with not with a compound like methane or ethane or propane, as those three that I wrote there, but actually a different one. And I'm gonna put the problem on the board. Let me see if I can. I cannot open the ebook for some reason. It's giving me an error.
I can't open it either. I can't even open the syllabus for any course either.
Something socket error or something?
Yes, that's right.
Yeah, I don't know what's going on. So please forgive me. I'm not gonna use the ebook. I'm gonna use a hard copy of the book that I have here. And let me try to describe the problem to you. So you have a compound. We have a compound that contains and we don't know the formula of this compound, we just know that the compound contains iron and chlorine. Let's put the symbols in parentheses, Fe, and it contains chlorine. Cl. So we know that much about the compound. Later in the problem, we are told that the amount in that compound of iron is 6.87 grams. So there are 6.87 grams of iron in that compound. How did we get that? It doesn't matter. It was analyzed by some lab, and that's the outcome of the analysis. The compound contains both iron and chlorine. It has 6.87 grams of iron, and it happens to have 13.1 grams of chlorine. 13.1 grams of chlorine. And that's all we know. So how do we get the empirical formula of this particular compound? We don't know the formula yet. We're gonna start by getting the most basic formula, which is known as empirical, and from there we're gonna see how close that is to the molecular formula. But we need to start somewhere. So what can we do with those numbers? Well, we can actually calculate moles. Because remember, when you have a formula, this CH4 formula doesn't tell you that you have 1 gram and 4 grams. That would be wrong. It tells you that you have 1 mole and 4 moles, or 1 atom and 4 atoms. Yes?
So that formula is the molecular formula, and then the other one is something different?
These 3 are molecular formulas of 3 different compounds. This formula is the empirical formula of that, of this, and of that. All of them match this minimum ratio. So if we divide everything here by 3, we get C1H4. If we divide everything here by 2, we get C1H4. So we'll get to that in a minute, Jason, but let's go back over there and see what we can do with this data. So there's nothing wrong with me saying, okay, let's see how many moles these 6.87 grams represent of iron. And that we can do. I'll show you how. You already know how, but I'm going to show you how. And the same thing we can do for the chlorine. How many moles of chlorine are in one analysis of this compound that contains both iron and chlorine? So, we're going to convert grams to moles. So this is a task, how to get an empirical formula. Okay? And the first step is always, from the grams, we're gonna get moles of each chemical. So let's do it first for iron. For Fe. How do we convert grams to moles? Anybody remembers? We had a diagram that tells you that to go from grams to moles, we need the molar mass. So we need to look at the molar mass of iron,
55.87.
55.845, right? So we look at the molar mass of iron and we say, okay, I have 6.87 grams of Fe. And I'm going to multiply or divide that by the molar mass. The molar mass is always in grams per mole. So I need to put the molar mass of Fe here flipped. In other words, I'm dividing by it. 1 mole of Fe is the same as 58 point, I forgot, 45. What are we going to use? 85. No. Yes, 85. This is crucial, you guys. So I don't want to move forward until we understand that we're doing nothing new. We're applying what we learned last week, converting grams to moles. For that, we need the molar mass, and we really are dividing. I'm using dimensional analysis because that's what I favor always. But that's what we are doing. Grams are going to cancel out, and I'm going to end up with moles of Fe. Now, before we do the calculation, let me set it up for Cl. We're going to do the same thing, except that we're going to use the amount of Cl instead of Fe. So we have 13.1 grams of Cl, and we're going to divide that by the molar mass of Cl, not of iron. So 1 mole of Cl,
35.45.
35.45. Thank you. Grams of Cl. And that comes from the periodic table, molar mass. So if we do that calculation, on the computer, I already have the answer here, so I'm just gonna copy it. For the top one, I get 0.123 mole. Of Fe.
0.37.
Thank you. And for the chlorine, as Jerry said, we get 0.370 or 0.370 moles of chlorine this time. Now we're not there yet, but now we know from this chemical analysis, we know the ratio of iron to chlorine in moles. Remember, the formula of any compound is a ratio in moles. 1 to 4, 1 to 4, 1 to 4. That's all it is, ratio of one chemical to another. In this case, if I write it like this, it's gonna look horrible, but I'm gonna put it. I have Fe. Why am I writing Fe first? Because that's the metal. You always write the metal first. How many moles do we have of Fe? 0.103. So I'm gonna put 0.123, sorry. And then Cl, and I'm gonna put 0.307, 0.307. So there is a formula for FeCl that reads Fe 0.123, Cl 0.370. However, we don't use decimal numbers in moles, right? We use whole numbers. The definition of empirical formula was the most simple whole number ratio of one atom to another. That's what it is. So how do we convert this into whole numbers? It's actually not that difficult. It looks difficult, but it's not. We're gonna look, okay. This number is larger than that number, right? 0.37 is bigger than 0.123. In other words, 0.123 is the smaller number of the two. This is what you're gonna do. You're gonna take the smaller number of the two, and then you're gonna divide both of those mole fractions by that smaller number. So we're gonna say 0.123 divided by 0.123 gives me a number, right? Well, it turns out to be 1. Because we chose to go that way. We saw the two numbers, we picked the smallest one, and we said, I'm gonna divide both of those numbers by the smaller one. And when I do that, I get a 1 there. If I do the same for these, I have to be consistent, so I'm gonna put 0.370, and I'm gonna divide that by 0.123. I'm dividing by the smaller number, both of them. What do I get if I do that? And the book has that number, or is it what you calculated? Okay. So the book has in fact what Jerry's saying. It's not a whole number, right? But it is. Why? Well, these numbers that you have here from an experiment that discovered how much iron and how much chlorine was in that compound has error. It's not perfect. It's never going to give you the precise amount. It's going to give you an amount very close to the reality, but not exactly the reality. So what we can say here is that 3.01 is almost 3. It's quite close to 3. So we can ignore those 2 digits and just say that the ratio of iron to chlorine is 1 to 3. So for every 1 chlorine, for every 1 iron, we have 3 chlorines. We're gonna ignore that. And now if I remember that ones are always implied. I get rid of the one, and this right here is the empirical formula of this compound. I'm not saying it's the right molecular formula. It may very well be, but it's the formula that you get by analyzing the mole amounts from grams and putting them as ratios, as whole number ratios. That's the empirical formula. So the empirical formula sometimes is the molecular formula, but sometimes it's not. At this point, we're done. This is the question. The question was how to get an empirical formula, and that's it. Now, whether or not that is a real molecular formula, that's a different story. And you know, I'm sorry for bombarding you with new terms, but now we are dealing not only with molecular formulas as a name that we had learned before, but now this new term called empirical formula. The reason why I shy away from this part of the chapter is because it accomplishes very little for what the goal of this course is. Nevertheless, it hasn't been eliminated. So I cover it with the caveat that, yeah, there's gonna be one or two problems in the homework dealing with this, but you should put your attention in some other matters. If this, you struggle too much with it, just ignore it. Losing 1 point in the homework is not gonna kill your grade, and if you lose 1 point because of empirical formulas and you want it back, I will put it back. Okay? I don't want you to struggle with things that are not necessary for you to, achieve the goal of finishing this course with some knowledge of chemistry. So let's just practice one example of what we just did, and then we're gonna see if we can actually take this one step beyond. So right now we're just writing another empirical formula for a different experiment, and we're gonna do it the same way. And see if we can come up with an answer just like we did that. So we have an analysis from a lab, and this particular compound, they actually given us a name. Phosphine, I think. Phosphine or phosphine has a composition from, actually this is a rat poison, of phosphorus and hydrogen. So the compound name phosphine contains phosphorus and hydrogen. And the analysis that the chemistry lab reported is that for every 0.456 grams of phosphorus, 0.456 G, you get 0.440 grams of hydrogen.
It is 0.44.
0?
Yeah.
Okay, thank you. So it has an extra 0, okay. So the lab analyzed this phosphine compound, and the outcome of that analysis is that it has 0.456 grams of phosphorus and 0.0440 grams of hydrogen. So what is the empirical? Empirical means experimental. Empirical formula. We're gonna do the same thing. We're gonna convert grams to moles. For both both phosphorus and hydrogen. So we have phosphorus, and we do the same thing that we did before. We put the amount of phosphorus that we have. So 0.456 G. And to go to moles, we need the molar mass of phosphorus. So we get that from the periodic table. 30.97. The book is using that, Jerry?
Yes.
30.97. Okay. So we're gonna say 1 mole of P is 30.97 G of P from the periodic table. And we're gonna get an answer. We'll get it in a second. Let's put the second chemical here is hydrogen. Hydrogen we have a smaller amount in grams, but what is it gonna be in moles? Well, we'll see soon. The molar mass of hydrogen is 1. So 1 mole of hydrogen. And let me use the number that the book is using. What is it using? What is it?
1.08.
1.08. Okay. 1.008 grams of hydrogen. And let's see what we get. So if you guys do the calculation, what is the number of moles of phosphorus? We put it on the screen so that everybody sees that. And I promise you, we're just gonna do this one more of empirical formulas and we're gonna leave it at that. We're gonna move on to the next topic. But it is important that you know what this means. So we're dividing 0.456 by 30.97. 0.14?
147.
Okay, well, let me do it myself here, just on my own piece of mind. 0.456 divided by 30.97. And that's gonna be the first amount in moles for the same first chemical. When we talk about significant digits here, you don't want to go beyond what you are given in the problem. So 1, 2, 3, 1, 2, 3 significant digits. Now these units are mole of phosphorus. And then we do the same for the hydrogen.
Would you be wrong to round the 4 up? Because you're going through significant figures?
These 4 up?
Mm-hmm.
Well, remember that this 0 is not significant.
Oh, okay.
So that will leave you with only 2 significant digits. So 1, 2, 3. Okay. 0.0, 4.0. 0.0440 divided by 1.008 gives me the other amount. So that's the moles of hydrogen. To 3 suffix, I'm gonna say 0.0437. Mole of phosphorus, of hydrogen. Now that was the first step, convert it to moles. I didn't label it correctly on the first example, but the second step is to write the formula. And I'm gonna write it with the mole proportions that I'm getting here. Not the final answer, but I'm gonna say, okay, to write, let me call it preliminary. Unquote, empirical formula. because then we have to fix it to the real one. And that means, okay, both of these are non-metals. So you could argue that you can put the H first and the P second. It turns out that in that particular chemical, the phosphorus is considered to be the first element because it's looking at hydrogen as being here, not there. How do you know that? By experience. There's no fast rule that I can give you. So you're gonna write P first and then H second. So the formula is 0.0147 and 0.0437. That's the preliminary empirical formula. Well, if we do the same thing that we did for the iron and chlorine compound, we need to find the smaller number of the two. So which one of the two is smaller? 0.0147 is smaller. So we're gonna do 3, find smallest number of moles and divide all by this number. Which I mean the following. I'm gonna say for phosphorus, it's gonna be 0.0147 divided by 0.0147 equals 1. For hydrogen, is gonna be this number, 0.0437 divided by the smaller number, 0.0147. 3.9?
2.9.
Or 2.9? 7?
9727.
Okay, let me leave it with 3 digits there. 2.97. And what do we do next? So we're not done. Now we have a whole number integer for the first element, for phosphorus. This one doesn't look like a whole number. 2.97 is not a whole number. However, it's very, very close to 3. Now, how close do you have to be? Well, if you are within 1/100th of a gram, or even 1/10th of a gram, you can round up. Well, these are moles actually, 1/10th of a mole or 100th of a mole. So 2.97, I have no problem saying this actually is about 3. If this number were 2.8 or 2.75, then we would have to talk. There's another trick. But for now, this is close enough to 3. Therefore, step 4 is going to be using those as the subscript. We write the empirical formula for phosphine, and is P1H3, 1 and 3. We erase the 1, and that's our final answer. That's the empirical formula of phosphine. Now, whether that is the correct molecular formula or not is not the question. That's not what we're trying to answer. We're trying to answer what is the empirical formula. So when we get to the homework and we find these empirical formula problems, we'll go back to this. Okay? But for now, what I want to do is move on to one more topic, and that is talking about molecular formulas. Now, before we do that, we need to talk about something called percent composition. can I erase this stuff? Okay, so I don't want to erase Avogadro yet. So the empirical formula is obtained experimentally. Most of the time you're not going to be having to do that, you're going to be needing the molecular formula. Now in the molecular formula, you always can look at the elements as having whole number ratios, or you can look at them as having percentages. Either way it works. So we're going to take a look at a particular chemical reaction. I'm gonna run out of time, but let me just start the topic and we'll finish it on Thursday. We're gonna take a look at a chemical reaction of a real chemical that it may not look real to you yet. But it is real. In other words, this is the right formula that I meant to write. It's not some imaginary or a mistake. So this is the molecular formula for a compound. I'll tell you the name in a minute. This is the molecular formula for something that you know as water, and this is the molecular formula for oxygen gas. So let's put here that this is a gas. This is going to be a liquid at room temperature. So little L, and this is typically a liquid at room temperature. Anybody knows what H2O2 is?
Water.
Looks like water, right? But it's not water, because water is water, and only water is H2O. So this is related to water. In Spanish, it's actually called oxygenated water. In English, it's called hydrogen peroxide. It's very simple. So this is, and Lisa said that, hydrogen peroxide. And again, I don't know in any other language other than Spanish, but in Spanish we say oxygenated water. One extra oxygen. So that's water, and that's oxygen. And this is a real chemical reaction that is taking place in your medicine cabinet. If you happen to have a bottle of hydrogen peroxide, not all of that is hydrogen peroxide, it's only 3%, but it doesn't matter. It's slowly changing into this. Now, if you want to expedite that reaction, make it really fast, now we're talking biochemistry, not chemistry, but biochemistry. You need something called an enzyme, and the enzyme will make this reaction go super fast. But in this discussion, what we care about is, first and foremost, balancing the equation, and then second, making some predictions.
Before you go on,
Yes.
why would you not call it dioxide?
Actually, maybe another name, and is correct, would be dihydrogen dioxide. Yes, sir.
Okay.
We can call it that. That would be the official name, actually. Hydrogen peroxide is a common name, but if you go to the pharmacy and you ask for a bottle of dihydrogen dioxide, which is the real IUPAC name, they're not gonna know. Well, the pharmacist may, but not most people. But you're absolutely right. The proper IUPAC name, systematic name, is dihydrogen dioxide. Just like this is dihydrogen monoxide. Okay, now let me get rid of the names, because what we need to now is count. So how many hydrogens do you see on this? Now let me remind you of what I said casually earlier, and I have about 2 minutes left, but here we go. These are called the reactants, or reactant. These are called the products. Sometimes you have one, sometimes you have several. Sometimes you have one reactant, sometimes you have more. In this case, you have one reactant, two products. This reaction is called decomposition. Decomposition is decomposing, breaking apart. You're breaking this apart into those two. But before we can even talk about anything more, we need to make sure that the amounts are correct. The formulas are right. I'm telling you, this is the right formula, that's the right formula, that's the right formula. But the amounts may not be. So we have to fix that. How many hydrogens do you see on the reactant side? We have 2 hydrogens. How many hydrogens do you see on the product side? 2. So the hydrogen amount is balanced. It's not a problem. We're going to leave that alone. Let's count oxygens. How many do you see on the reactant side? Also 2. Not 20, but 2 O. And on this side, what do we see? Unfortunately, we don't see 2. We see 1 plus 2, 3 oxygens. We need to fix it. We need to make this side have 3, and so that this one has 3 also. Or we need to do something else. Now, to make a 3 is a tricky task. So this is what I want to propose to you. And actually the procedure is known as trial and error. We don't have a fast way of doing this other than trying something and see what happens. If it doesn't work, we try something else. So trial and error.
Unless you blow up the lab.
What?
Unless you blow up the lab.
Yeah, unless you blow up the lab, right? So let me change this number of oxygens to an even number. So how do I get not a 3 or a 5 or a 7, but a 2, a 4, a 6, or an 8? Keep in mind you can do anything that you want except change the formulas. This has to stay H2O2, this has to stay like that and like that. But I can certainly do this. I can put a 2 here. So but let's concentrate on the oxygen for now. You're absolutely right. It does changes the hydrogen, but that's why it's trial and error. So if I put a 2 there, what is the total amount of oxygen now? 2 times 1, 2, plus 2, 4. Now I have an even number, which is what I wanted to accomplish. Now if I go to this side, that doesn't work, right? Because I still only have 2 hydrogens. Well, how do I get, 2 oxygens. How do I make this a 4? Put a 2 here, right? I cannot change the formula, but I can actually change the amount. So 2 times 2 is 4 oxygens. So now my oxygen on both sides is balanced. But I have to do 2 things, added a 2 here and a 2 there. Now let's count hydrogens. 2 times 2, 4 hydrogens. Now this I was worried because this had changed the hydrogen. Yes, it did. But look what happens now. 2 times 2, 4. Now we have balanced also the hydrogen. We have a balanced chemical equation. This is not the same as 1, 1, and 1 because we cannot reduce this more. This would become 0.5 if we were to divide everything by 2. So that's the simplest chemical representation of this reaction.